control, but please be patient. So we will be continuing this. So let me start from the beginning again, as this is interrupted. So I'm using, for further explanations, for better understanding, I'm using the cool pack. Okay, cool pack, and let me draw a same cycle like what you have learned here. Okay, let me draw a similar cycle as like what we have drawn here, but this time it is a bit professional, okay, and technical. Okay, yeah. So again, pH diagram. And here you can say list of refrigerants, all the primary refrigerants, and I'm considering here same for our case as previously discussed, the more eco-friendly hydrocarbon refrigerant, but you may have some safety issues, but you have to take care of those. So the refrigerant we select R600A. Okay. As I mentioned to you, this one you can find even in your houses, but purity is not that. But this is for refrigerant, it should be perfectly pure, almost 100%. Almost 100% purity level is important for refrigerant. So, as we have discussed, we realized how important the chart of pH or pH diagram. And here for this system, with 4 major components, we have identified this cycle on this pH chart. So this is we call pH diagram, and 7 points are well identified. Okay, and also the shown with the arrows, delta T, 3 delta T's, LSC, SSH, and DSH are mentioned here. We will see how practical and how technologically important these are. That's why when it comes to technology, you learn something up to sufficient depths to apply this. So this is what I'm doing here. So I'm going to select for this R600A, okay, understanding transport, I put here. Because once you understand transport, everything is done. Vapor, compression, cooling, technology. Okay. So here you are always referring this or this. Okay, you are referring this. So you have evaporator, the low pressure side, okay, and the high pressure side, unloading side. So now I'm going to add this data here. Evaporator, let's say it's mentioned in our case, the temperature is 10 degrees Celsius. 10 degrees Celsius. Unloading side, it is 45. Okay, it is 45. As we have seen here, see 45 degree. And the corresponding pressure will be calculated by the system itself. Superheat, as I mentioned to you, the superheat at the loading side is the suction superheat. Okay, SSH, suction, superheat. Delta T, we consider temperature difference of the actual and ideal, T1 minus T1 dash. So when we design a system, we have to consider this as well. So let's say for the safe side and also as optimal, we will look for 5 degree superheat. Okay, 5 degree. Later I will change this and I will show you, right? And some cooling for the unloading side. Subcooling for the unloading side. As we know here, this is for the unloading of heat. So this is at the high pressure side. Okay, this at the high pressure side. This delta T, LSC, I put liquid subcooling. So that is how low this is cooled below the limiting point 3 dash. Okay, below the limiting point 3 dash for the safe side of the designs. Okay, so if subcooling here, let's say for the safe side, we will take again 5 degree. Okay, so superheat, suction, subcooling, okay, liquid subcooling. So we have to, these are design parameters. So no pressure drops we consider. And you can see here isentropic efficiency. Okay, isentropic efficiency. Okay, that's why you have learned about this. So I will take a snapshot of this as cycle inputs. See, even I will make it more better. So you can see R600D cooling cycle, inputs. So now you can see inputs means, so design inputs, okay, inputs for the design. So here evaporating temperature means unloading, transport. Sorry, at loading it is coming at 10 degrees C. Unloading for this loaded heat, transport at 45. You have the superheat 5, subcooling 5. Okay, superheat 5, subcooling 5. So if I further explain this, this is your subcooling. For you to remember, superheat, here, again you can see it, superheat connection. This is a superheat for you to recollect this. So these are important. Okay, and 10 degree and 45 degree. That is here 10 and 45. You can see it here. So these are something as designers we should outline. Okay. As designers we should outline these figures. Okay. So what is your transport unloading temperature? What is your transport the loading temperatures? We should outline those. The pressures. Yes. So these are the basic data, and now we have added all here. See, all added. Now I'm going to draw the cycle. See what happens. Can you see this? Okay. Can you see this? So this is the cycle. Okay, this is the cycle. So if you compare this with what we have outlined, okay, we have outlined this. With no much of knowledge, but with the basic, okay, with the basic analysis, we have outlined this. So let me take, I have to copy this, cycle. So copy, I will copy this, copy. This is already done, including the coordinates, yes. So let me paste this and see what happens. Oh, not that one. That is let me look into that again. Okay. So after generate the results, okay, coordinate points. Let me see. These are the coordinate points. 1, 2, 3, 4, 5, 6 points are there. Okay, 1 point is not there. So I will copy this. Maybe copy this. points 1 to 6. Okay, there can be 15 points here, 1 to 6. Okay, 1 to 6 points. Later we will see what this 1 to 6 points are. Actually, we know this already, we have discussed. So that's it. And the values are there, our inputs. So, and here the calculated results. You can see no dimensions because we have not put other details. Calculated results, you can see. We will try to understand this. Loading QE, evaporate. Unloading energy QC, all per kg transport. COP means, yes, you have to consider W as well. So this is your work because isentropic efficiency is 1 based on this. Okay. So this is your W. And you have the pressure ratio as well. So these are the calculated values. Okay. These are the calculated values. And here you can see the H values are here. H values are here. So you can see the points 1, 2, 3, 4, 5, and 6. Okay. So lowest 4 evaporate entering. Okay. 5. Let me see. 5 and 4 and 5 here it's the same. 6 is 577. 1, 2, 3, 4, 5, 6. 1 is 577 again. 2 is 617. Okay. So let me do a little calculation now. What is W? W is, if you can remember the cycle, 1, 2, 3, 4. Okay, W is H2 minus H1. We have learned this. Okay, now I'm going to take this. See, I have learned, we have shared everything. That's why going through this. This analysis, analysis. Let's say corresponding points here. W, H2 minus H1. Here should be 617.134 minus H1 is 577.584. 4. Okay. I failed these 2 other points in this cycle. So if you go to calculate, $39.55. Okay. So this is 39.55. Can you see? The system calculated W, 39.55. Okay. You can see W here, H2 minus H1. So the other value, QE, or this is loading. So after loading and before loading, because before loading there is an energy level at the empty conditions. Okay, that is 295. Okay, 295. 5.182. That is H4. Okay, so this should be deducted by H1. H1 is 577.584 per kg transport. Okay, so this is kilojoule per kg. Yeah? Malli. Okay, Buddha, sorry. So QA, let's say this one, what's the value? I believe you can see this screen sharing. So I take the calculator. This one, 282.402. See, you can see 282.402 here. Okay, 282.402 kilojoule per kilogram. Then QC, unloading. Okay, unloading. So also should be in kilojoule per kilogram. So QH we mentioned here, that is H2 minus H3. H2 is 617.134. See. Until entering the metering device after liquid subcooling. Okay, that is QC. So that is unloading, means condensation is taken place. Same as for loading, evaporation is taken place. Evaporation means getting the liquid energized. Okay, so I have explained this to you a lot. QC 617, that is H2 minus H3. H3 is, let's say here not H3, this is H4. Yeah, we put the value here. H2 and H3 are the same here. Later I will explain. Here should be 295.182. 295.182. Based on the data, I can see it. So let's say this value. Okay, because here H1, H2, okay, H3 is a different one here. H4 is entering the capillary, H5 is leaving the capillary. Yeah, here. Okay. So let me open the calculator. (321.952) is the QC. See here, 321.952. So you can say it. 321.952 kilojoules per kilogram. Okay. Then you have COP, refrigeration. So here your objective is removing heat. This much QE against the work done. 39.55. Okay, so that is 284.402 divided by 39.55. Okay, we'll see the answer. So I'll copy this to the calculator again. Let me open up the calculator, paste it. Let me get the answer. 7.140. Do you know the beauty of this evaluation? We are getting independent software and we are putting our theory on that, and we are seeing the results are the same. So you know that you are learning something, knowledge very correct, okay, with more understanding. So that is the point. Pressure ratio. Pressure ratio. So what's the pressure ratio? In this case, you have, see, 6.102 bar divided by 2.219 bar. 6.102 divided by 2.219. 7.7498. Okay. So you got to this. See, 7 point. Okay. COP value. So sorry, pressure ratio. That is 7 points. So I will put here this way. P, see 2.219. This is the evaporate, low pressure. See this line, low pressure line. Later, let me take high pressure, 6.102. 6.102. See 6.102. Then 2.219. You can see 2.219 somewhere in this calculations. 2.219. Divide both. Okay. 2.74 here. Let me see the evaluation here. So 6.102 divided by 2.219, you will have the COP value here. Anyway, it's shown as 7.14. Okay. 6.102 divided by 2.219. So let me take this, clear this, paste. 2.749. Now see here, pressure ratio is 2.75. So 2.749 is very close to 2.75. Okay, this is the pressure ratio, bar divided by bar. It's a unitless value, same like COP. So all are calculated, and the system also for this calculation. So we are learning some useful theories. Okay, and I will highlight something here.
Excuse me, sir.
Sorry. So if you refer to the PowerPoint file here, point number 3 is a design point. Point number 1 is a design point because you are defining the superheat and the subcooling. And this line number 2, 3 is a design line, design point. Line number 1, 4 is a design point, design line, okay? So you know 1 and 3 in your design. And also you should know the isentropic efficiency. Isentropic efficiency, you can see here. You have to define this. Upfront, you have learned about this isentropic efficiency because there are reasons. Now I'm going to do the same, okay, with edit, select cycle, select curve. I don't know. Yes, select curve. Cycle is this. Sorry, that is not the cycle. Okay, this is the cycle auto loaded 10, 5, 45, 5. Okay, this is auto loaded. So now I'm going to change a bit. Okay, I will change superheat to 0, means bringing that point here 1 to 1 dash. Subcooling, I will take this to 0, means bringing that 3 to 3 dash. I will do updates. Okay, I'm going to draw the cycle. Oh, something went wrong. To do this. So I have issues with that. I have the issues here. Cool pack. I will stop. Cool pack. I will stop. Okay. Let me leave it. Okay. Let me leave it. They're quite funny. The things are happening. Okay, finally done. Give me a second. I'm going to okay. So let me share with you what happens. Okay, let me share with you what happens here. Uh, I hope you can see this. Now see, because of this, considering suction 0, what happens is after compression, this becomes little more with liquid. See, can you notice this? This is not acceptable because compression process, within the compressor, if liquid is formed, you know the compressor can damage because liquid cannot be formed during compression. That's why a little superheat is very important. Okay, so this is another lesson. So this is another lesson. Oh, this is another lesson. Let me copy this, only this part. Okay, you can see. This one. This one we have issues because of this point inside the vapor dome. Point 2 should be outside. Okay, that's why when you are designing, it is very important to look into this. Okay, when you are designing, maybe a little bit advanced, I don't know, Pita, but these areas you should learn. That's why I have to explain this to you. If you don't know these things, no point. Yeah. So that's why it is very important for you to have this superheat. So what I will do is now I'm going to delete this. Edit, delete curve. Yes. Yes. Okay. And now I'm going to draw a new cycle. Okay. Evaporating 10, condensing 45. Save. Superheat I will put, we have to put minimum 5, so I will put here 10 because even 5, you can see even 5 superheat. This is almost very close to this line. So I'm going to change this 5 to maybe 10 superheat. Subcooling, it's okay, 0. Okay, 0, okay. Now you draw the cycle. See, you can see this one. Draw the cycle. Why here 2 points? Subcooling 0. Right. Yes. Then let me start new. So I will go to cool pack. this? pH. (600A). Just the one. Draw cycle. Evaporating 10. Condenser 45. Superheat 10. Okay. Degree of superheat. It's a difference only. T1 minus T1 dash. Subcooling 0. I will do some updates. See, the values are automatically calculated. We can draw the cycle. See the cycle here? Just nice. Draw the cycle. Okay. Select curve. This is the curve. Yeah. So these are the values here. Okay. Same way, you can even copy this. What copy? No, not this one. Copy. So this is okay. So you can see the QE, QC, COP, and WN pressure ratio. So if we are asking this kind of values by giving some design points, as I mentioned, this is a design point I'm circling here. This is a design point, this is a design line, this is a design line. So you can mesh this with your values. Here isentropic efficiency I put as 1. Okay. Isentropic efficiency we put as 1. So if we delete this curve, okay, I'm going to delete this. Because I'm going to draw one more here with this case. Again 10, same like previous. Condenser 45. Superheat 5. Subcooling 5. Isentropic efficiency I will put 0.8. Okay, draw cycle. This is the cycle. Okay, isentropic efficiency 0.8. So we have 2 cycles. So I don't know what is this. Why we have 2? Yep, including the previous one maybe. Let me close this. Okay, let me draw cycle. 10. I have to update the software. 45. 5. Subcooling 5. Isentropic 0.8. Update. Draw cycle. We need to update first. So you can say this. Okay, you can say this. Select curve. This one. Cycle. This is the value. So show info. So these are the information here. Okay, these are the information. And the coordinate points are here. So let me take this coordinate points. I have to take what happens. Yeah. Give me a second, Bhuta. We have little issues for the software. That is not well presented. Yeah. So I will show you one thing only. Now here the isentropic efficiency is 0.8. Okay, let me show you just one thing here. So see, W value is, what's the W value? 49.435. All same conditions, inputs, only efficiency is 0.8. Let's say what happens is, now this is 49.135. I will go to this and I will go for this evaluation. For this case, here isentropic efficiency 1. 1. Okay. Next, isentropic efficiency 0.8. So I'm getting the work done only. I have little issues of copying this, that's why. W is 49.437. Okay, W 49.437. So I will take that W is 49.437. Okay, this is W, kilojoule per kilogram. So actually what happens is, so this 0.8 should be equal to, okay, this 49, let's say this is 39.55 divided by 0.8, because means it is isentropic, means no entropy. Okay, no isentropic means no irreversibilities, let's say. Now the situation is isentropic, it is not, efficiency is 0.8. If you go to calculator, if you paste this value 39.55 by 0.8, you have 49.435. See, 49.435. So kilojoule per kilogram. So almost the system value, 49.437. Only 0.002 variance. So you have learned about isentropic efficiencies. Okay, yeah, this is about isentropic efficiency considerations for the cooling cycle. Okay, so this is, so accordingly, everything change. Okay, let's see, this is W. Okay, your QE has no change. Yeah, because your subcooling and superheat all remains the same. QE is the same. Try to understand. And this is W. So your QC is unloading one way from energy balance. QE plus W. What is QE? This. What is W? 49.4375. 437. See the value. Use the calculator. 331.839. Kilojoule per kilogram. Is this right? Look into this. Oh. QC, 331.839. You can see it here very clearly. 331.839. Okay. 331.839. So see 331.839. Even using energy balance. So here also, if you look into energy balance, it is automatically QC is QE plus W. Q is the same. W becomes 39.55. 39.55. We have only 16 students. And there can be a value by right should be same as QC. But to verify this, let's go to the calculator. This to get the value. Copy. 321.952. See 321.952. That is the energy balance. Okay. Now you can see that the Coolpack software we have used for little evaluations. You felt that our knowledge is quite practical, important, and also quite how to say, useful. Okay, quite useful. So this tells all, because the Coolpack software is for the evaluation of the real systems. So you are using this and we are verifying our knowledge by using this. Okay, I'm not promoting Coolpack, but it's a free software, you can use it. So that's the situation of this. And now I'm going for a different case now. It is same. I have to reinstall this, that is one way. Now let's say for the same situation, okay, for the same situation, same like PS. Another important is TS diagram, because you have noticed that isentropic efficiency came there other than the temperatures and the pressures. So here, so we will look into how to incorporate S into these charts. So back to R600. It's a similar one. Okay, it's a similar one. You can see the liquid vapor dome. Towards right, all gas superheated. Left, it's all liquid. It's all liquid. So, any chance to draw here? No chance to draw. No chance to draw. But anyway, why we cannot draw here? Let me draw, yeah, in this way. So I will take this TS diagram. I will take the full scale. Entropy unit also you know. That's why you need understanding. Yeah? Scale. Temperature, entropy. Okay. TS. Quite interesting. So temperature entropy. So let's say I will take 0.1. Okay, 0.1, sorry, 0.2, 0.1. Okay, I will take 0.1, same way here. So I will take this. Similar approach. Okay, this is pH. So we need 0.1. Yeah, okay. So we know the pressure and the temperature. Or yeah, we know the pressure lines first. Okay, pressure lines first. So pressure lines generally for the constant pressure here and the constant temperature. So let me draw the pressure lines first. Pressure lines in the liquid vapor dome. Pressure and temperature, same way, no change. So any pressure line should go flat. Any temperature line should go flat. Okay? Here. So after that here, what happens is, since this is TS diagram, S is going high, and from here onwards, there will be temperature rise, 5 degrees superheat, constant pressure. Try to make sense. Entropy rise. Okay. Entropy rise. Constant pressure line. Let me draw this way. Constant pressure line. Okay. Red color lines. One should be constant pressure lines. See, constant pressure line. Okay. And this constant pressure line goes like this. Okay. Constant pressure line. Constant pressure line goes like this. Let me see. This is 5 degrees C. Okay, 5 degrees C. So after that, the compression starts isentropic. It comes here. So this point will not go till then. It drops like here. Okay. So here, some cooling, temperature dropping, entropy dropping, constant pressure line remain. Okay, something like this maybe. Okay. Then here to here, it should be something like temperature dropping, enthalpy remains, but entropy there can be a slight decrease. So this is the point. Same enthalpy but different entropy. So let me explain this in the next session. Okay, let me explain this in the next session. But this is the constant pressure line. Yeah, but anyway, we have to leave it here. Okay. Okay, to have this line, no issues, constant pressure. Then this goes like this. So this is how we see it is. So anyway, this way. I will just extend this. Okay, it's something like this. See, 1.0 comes like here, 1.0, it goes like this. Constant pressures, unchanging pressures. So constant pressure lines are like this. But in pH we have the straight line because there it is the constant pressure because vertical axis is pressure. So that's all for today, I believe so. So this is how isentropic. If it is not isentropic, with some efficiencies, what happens is this may go like this. Then your line alters a bit. This constant pressure line continues and meet this compression here. Okay, like this. Further slanting if possible. bit saying this, it's like this. Okay. Like this. Yeah, that's all. So we will discuss this TS diagrams afterwards. So we will discuss this TS diagrams afterward. So we have to spend another session for this TS. So after learning TS, we are going for a little, of course, we have done some evaluations. I will give you an assignment on this. After that, we will look into power plants. And before that, if any more we need, we will discuss in the cooling systems. And I should mention you about the liquid cell before winding up today. Okay. Liquid cell is something that is necessary for flashing. Okay, liquid cell is something that is necessary for flashing to take place. That's why liquid should turn into vapor partially, and the temperature from the liquid itself, the energy from the liquid itself pass to the evaporation, and the temperature drops and vapor forms. And the liquid is important. If no liquid, no flashing. If there is a mix of liquid and vapor, your flashing is not effective. So always we have to assure that entering the capillary or expansion device, there is 100% liquid. So 3 dash liquid, 3 also liquid. So entering, if I draw this way, let's see, if it's a metering device, so let me draw it. I'm going to draw a flow restriction. Something like this. See a little flow restriction. So here, a bigger pipe shown. And for this case, here, there should be 100% liquid. And of course, entering this, before entering, this can be a big pipe. Let me show you it. Come like this and go down. Go down like this. Go down like this. Okay. So it is very important to assure this liquid cell. Okay. This liquid cell. So here, the other side, after that, let's it's returning. Okay, it's returning. It's perfect liquid seal. A second. Yes, it's perfect. So what happens is, after that,